Okay, so here are the solutions to this old test 4. So we've got this second order DE, and we're going to solve it about x equals 0 using a power series. Okay, so the first thing we always assume, of course, is that y equals the sum from n equals 0 to infinity, a n x to the n. Sometimes we use t, sometimes we use x. I specifically said to use x here, but honestly, it really doesn't matter. We take the derivative term by term. The derivative of x to the n is n x to the n minus 1. Now on this one, we could, if we wanted to, since when I plug in n equals 0, the first term is 0, I could, if I wanted to, say, well, this guy's going to start at 1. So I could change that to an n equals 1. But because it's already being multiplied by x, see, I'm kind of looking ahead here. That's being multiplied by x. I'm going to get an x multiplied in here. That's going to raise this back up to x to the n. So that won't be necessary. In fact, that would be harmful if I change that to an n equals 1. I need all my powers to be the same, and I need all my starting points to be the same. Okay, y double prime, taking this guy's derivative, I'll get an n minus 1 down there, and the power will become n minus 2. And again, if I plug in an n equals 0, I get 0. If I plug in n equals 1 right there, I get 0. I could, if I wanted to, start my counter here at 2, since the first terms were 0 anyways. Okay, so that's what I'm going to do with this one. I'm going to change this to a 2. All this is going on in the background. This becomes a 2 because I want this to be x to the n. I need to raise this up by 2 to match this guy. So I'm going to start this at 2 since the first two terms were 0 anyways. Raise all of these up by 2, drop that down by 2, then this will go back down to 0, and this will go up to x to the n. That's this first expression right here, y double prime. Then I have 3x times y prime. So again, the x, I don't need to play that game with this, the y prime expression, since that x is going to raise me back up to x to the n. And I brought that 3 in. And then just plus y, so just regular y, that goes here. Now everybody has a power of n, and all my n's start at 0. So I can squish everybody together into one sum. The only way this entire sum can equal 0 is if it equals 0 for all powers of x. That means every coefficient must be 0. So just adding all these coefficients up, they must add up to 0. So there's my recursive formula. I just mathematically, algebraically solve this equation for an plus 2. It's a second order DE, so the first two coefficients are always going to be free. Remember, A0 is y of 0, A1 is y prime of 0. Always, as long as we're expanding about 0. And we weren't given those initial conditions, so those will just be free. Now I start plugging in values of n. Remember, your value of n does not match with your a subscript. If I plug in n equals 0, that's going to give me A2. So don't focus so much on this number. Look at that number, A2, and then just plug in n equals 0 everywhere. Will be negative A0 over 2, and so forth. So we do that for a few powers. The question asked for the first 4 terms of each one. Y1 is all the stuff with A0, Y2 is the stuff with A1. I didn't come up with this numbering scheme. I know it's silly. So let me go down to the answer. Y1 is all the terms that have an A0 in them. Y1 is all the terms this should say y2. That's a typo right there. Y2 is all the stuff that has a1 in it. I think it's silly. We should call them 0 and 1, but that's what it is. And then our general solution is y equals y1 plus y2. Okay, so again, try this on your own. These are the solutions I got. Okay, now we're solving this second order DE. Again, about x equals 0. We are given some initial conditions. That's going to be a0, and that's going to be a1. Then we're going to plug in a value into that power series we get, and we're going to compare that with what the actual solution is and see how close our power series gets us. Okay, so I wrote this question and I interpreted this: find the first 5 non-zero terms. I interpreted that differently than a lot of students did when they solved this, when I actually gave this. And honestly, the students probably had a better interpretation of it. So you'll see what I mean in a minute. Okay, so first, like always, we assume y equals this sum. Then our second derivative will be this. And I'm looking ahead. I don't have any extra x's in here. So these guys will not have the same power on them. See, I've got an n and an n minus 2. I need this to go up by 2. But the only way to do that is to drop this down by 2. So I didn't even start counting until 2, since n equals 0 makes this 0. N equals 1 makes that 0. I might as well start counting at 2. Then I can raise all of these up by 2. Notice everything went up by 2 while simultaneously dropping this down by 2. You can't change these without changing that. Then I can squish everything together into one sum. You're only allowed to do that if your powers match and your starting points match. Otherwise, you have to go through more work. The only way this can equal 0 for every value of x is if every coefficient is 0. So that means this expression here in the brackets must be 0, which gives us our recursive formula for an plus 2. Okay, so a0 and a1, since it's a second order, the first two are free. They won't be determined by the recursive formula. If I had a fourth order, I would have 4 free coefficients. So I start plugging in values of n, and it said find the first 5 non-zero. So I found up to a4. In fact, I actually found up to a5, but I didn't need it because it said find the first 5. So I found the first 5. That's how I interpreted this sentence right here. Now I'm going to plug in the initial values. Now, this right here means a1 is 0. So everything that had an a1 in it is going to be 0. So that guy's 0, a1 is 0. That guy is 0. So once I plug in my initial conditions, I only ended up with 3 terms. So students, when they took this test, they interpreted that, oh, I need to find more because he said find 5 non-zero. I've only got 3. I need to get a couple more in there that'll have this guy in them to get a total of 5. And that's probably the better way to interpret the question. So if you were to go and have an a6 or x to the 6th and an x to the 8th in here, you would get a better approximation. And honestly, it's probably a better answer to the question. Okay, but I stop there. So I get this 4th degree polynomial as an approximation to the actual solution. Now the actual solution is this. That's the power series expansion of 3 cosine of 2x. So we're going to plug in this value pi over 12 into both the polynomial and the real solution. We're going to see how close we got. So you could check these on your own. If you plug in pi over 12 into that fourth degree polynomial, you get this number. If you plug it into the actual solution, you get 3 root 3 over 2. So my error, just one bigger minus smaller, I guess that one minus that one, was really small. If we had kept a few more terms, the error would have been even smaller. Okay, now we're doing this much harder. I would argue power series, not much harder, but there's a little more work here. So I've got this expression out in front of the y double prime. So I'm going to have to distribute that. Okay, so we start same as always, assume the solution is n equals 0 to infinity, an. There should be an x to the n here. I should say x to the n. I'll go in and fix this document. Here's my derivative. Here's my second derivative. Now I'm going to need both versions of this. So here I played that game where I said the first two terms are 0 anyways. I might as well start at 2, raise them all up by 2, drop that down by 2. Here's another way I could write that. But I've got this x squared term also. X squared times this one will bring me back up. Just, you know, when you multiply like bases, you add the exponents. N minus 2 plus 2 more. I'll get an x to the n from this. So I'm going to need this version for that guy and this version for the 1 times that. And then looking here, I've got an x multiplying y prime. So I don't need to play any kind of games with this guy. X times y prime will bring this back up to an x to the n. Everybody's going to have the same power. Okay, so here's the 1 times this plus the x squared times this one, and then minus the 5x times this one. Everybody has x to the n. Everybody starts at 0. That gives me this recursive formula. So I squish all this together into one expression. The only way that can equal 0 for every possible x is if every coefficient is 0. So all of these coefficients must add up to 0. We solve for an plus 2. Here I've just cleaned it up a bit. These say the same thing. First two coefficients are free because it's second order. And then start writing up the solution. You should check all the details here. Here we end up with, this was not because of any initial values, just A2 happens to be 0 here. So here's my Y1 and my Y2. Remember, Y1 goes with A0, Y2 goes with A1. Okay, this question wanted us to use Euler's method. So we're given a delta X, an H, and a starting point. So I did this in Excel. Okay, so we can actually do this. We can say, okay, here we'll have our X's and our Y's. And we're starting at 0, so equals 0. And then I'm going up by 0.4, so equals the previous value plus 0.4. A huge delta X, by the way. So this approximation is not going to be very good. And I want to go down until I reach 2. Up 1 more. So that's what it asks for here. Now each Y value, remember we have to know how to use Euler's method. We're going to start at 2. That's our initial Y. Then each new Y value will equal the previous Y value. So I actually just clicked on that cell. Plus H, my delta X, 0.4, times the derivative at the previous value. So my derivative, I'm going to need parentheses here, will be the previous X squared times the previous Y minus 3 times the previous y. Close my parentheses, hit enter. And then I can just drag that down. I could even just double click on it, or I could drag it down. And I get all my y values. Same things I got there. Okay, so we could have done that by hand, or like you're going to have a question like this on your test, something where I ask you to use Euler's method. You do not have to do it by hand. Those can take forever, and there's so many ways you can type that into your calculator wrong. It's perfectly fine to use Excel and just do what I did, copy and paste this table. Like I could just grab this entire table here. Oops. Just highlight it and hit Control C, and now I could copy and paste that into a document. Okay, this is the actual solution to that DE. I want to know how good this solution was. So by the time I got to 2, this is what Euler's method said the answer should be. If we plug 2 into this, we get that. Those are very far off. It's Euler's method gave us a terrible approximation here. Those aren't even close. And the reason for that is my delta x was gigantic. If I had done like 0.01 for fun, let's do that. So let's say this equals plus 0.01. And then redo these. And then I need to scroll down until I reach 2, which I think would be about 201. Oh, okay, well, something went wrong there. Let me pause this and make sure I get that right. It was right here in my formula. I was still using the old H or delta X. I need to change that. And then redo all of those. And by the time I get to 2, 0.066, and the actual answer was at 0.071. So still not perfect. This may be what we call a stiff DE, where Euler's method does not work great unless you use incredibly small delta x's. Because 0.01 is pretty small, but still not nearly as bad of an approximation as what we got using 0.4. Okay, and then the last question I had on this old test was doing a slope field and doing it by hand. And the idea I had in my head was, I don't want you to just type this in, which we could do here, and just go slope field plotter. I think I like the Desmos one better. And I could just type in here, oh, what was it? Negative x over y is y prime. I mean, sure, this is a good thing to do to get an idea what the answer is going to look like. But in the past, all I've had people do when I ask them to plot a slope field is just do this and then try to copy that on their paper without actually calculating any of these points, the slopes at these points. So on this old test, I gave you a bunch of points and I wanted you to calculate the slope at each of those points. And all those points I calculated fall on this particular solution curve I'm talking about down here. So I found a bunch of points that live on there, and I wanted you to calculate the slope, just literally negative x over y. Plot all of those points with a slope, a little unit vector going at this particular direction at each of those points. Like at many of these points, like at the point 0, 4, we get an undefined slope. That means our vector at 0, 4 is going to be straight up and down. In this case, it'll be pointing down. And then once we get all of those, I wanted you to pick a bunch of extra points, just kind of make some up, and then use that to estimate what's going to happen if I start here. Remember, the whole point I don't know why this is not, maybe it wasn't Desmos, maybe it was the other one that graphs a solution curve. Is it GeoGebra? Yeah, GeoGebra is the one that graphs a solution curve. So this was negative x over y. So I could start with a point at negative 4, 0. Oh, and look, GeoGebra is not going to graph that because my slope is infinite there. It doesn't know what to do with it. Oh, so see, GeoGebra is going to fail me here. That's why I wanted you to do this by hand and get a solution curve that kind of looks like this. Now, see, look, it's getting confused. It doesn't know what to do with those points here on the end where the slope is infinite. So it's trying to connect it up. It's guessing, and it's connecting it to other solution curves. Our solution curves don't look like that. They're circles. The actual solution is a circle of radius 4. So this particular solution curve would actually go all the way around. If we want it to be a function, it would be the top half of that. And these numerical solvers online are not going to pick that up, though. So that was the point of this question, was doing one by hand and realizing that this thing's going to let you down a little bit. Like, that doesn't make any sense. But what ended up happening was people did this and they tried to draw crap that looked like this. I mean, look at that. That's not even right. These are not all on the same solution curve. So I ended up getting a bunch of answers that look like this, and it's not what I wanted at all. So when I write the new version of your test, there will be something with slope fields in there. But this one turned out to, look at all this. It just turned out to be a little messier than I intended. So then, just to finish this up, the part C was solve the DE. I mean, it's separable, it's linear. There's a bunch of different ways we could solve it. Just solve it, get the actual solution, and compare that with that curve that you drew a minute ago. It's a good place to stop.